Welcome to video 1 for this unit on dilations, similarity, and introducing slope. In this video, we're going to focus on dilations. Here is a point P and triangles A, B, and C. What do you notice about these triangles? You may have noticed that the three triangles seem to have the same three angles, but are different sizes. Let's add some lines to make the relationship between the three triangles and point P clearer. Earlier, we learned about three rigid transformations: translations, rotations, and reflections. This is an example of a different type of transformation that isn't rigid. It is called a dilation. Here is what a dilation of triangle B to triangle A looks like. And here is what a dilation of triangle B to triangle C looks like. A dilation is a transformation in which each point on a figure moves along a line and changes its distance from a fixed point. The fixed point is the center of the dilation. All of the original distances are multiplied by the same scale factor. Here is a circular grid. The radius of the smallest circle is 1 unit, and the radius of each successive circle is 1 unit more than the previous one. A circular grid like this one can be helpful for performing dilations. Here is triangle A, B, C, and triangle A', B', C'. Triangle C' is a dilation of triangle A, B, C. To perform a dilation, we need a center of dilation, a scale factor, and a point on the original figure to dilate. In the picture, P is the center of dilation. The center of a dilation is a fixed point on a plane. It is the starting point from which we measure distances in a dilation. In this example, the scale factor of the dilation is 2. That means that each corresponding point stays in the same ray from P, but its distance from P doubles. That is, since the circles on the grid are the same distance apart, segment PA' has length 6 units, which is double the length of segment PA. Let's look at a dilation done without a grid. Here, point A is the center of the dilation. If we were using a circular grid, point A would be in the middle, and points B, C, and D would be on the same line. How can we find which point is the dilation of B with scale factor 2? Since the scale factor is larger than 1, the point must be further away from A than B is, which makes C the point we are looking for. If we measure the distance between A and C, we would find that it is exactly twice the distance between A and B. A dilation with scale factor less than 1 brings her to the center of dilation. The point D is the dilation of B with center A and scale factor 1/3. That is, the distance from A to D is 1/3 the distance from A to B. Square grids can be useful for showing dilations. The grid is helpful, especially when the center of dilation and the points being dilated lie at grid points. Rather than using a ruler to measure the distance between the points, we can count grid units. For example, suppose we want to dilate point Q to point Q' with center of dilation P and scale factor 3/2. Earlier, we used a ray starting at the center of dilation to figure out the location of the image after the dilation. However, we can use a square grid to show a dilation as well. Point Q is 4 grid squares to the left and 2 grid squares down from P. Where will point Q prime be on the grid? Since 3/2 is larger than 1, point Q prime will be further from point P than point Q is. Using the structure of the grid, we can scale the horizontal and vertical distances from point P to point Q by the scale factor of 3/2 to find the location of point Q prime. Since 4 times 3/2 is 6, and 2 times 3/2 is 3, point Q prime is 6 grid squares to the left and 3 grid squares down from point P. Sometimes the square grid comes with coordinates. The coordinate grid gives us a convenient way to name points, and sometimes the coordinates of the image can be found with just arithmetic. For example, to make a dilation with center 0, 0 and scale factor 2 of the triangle shown, let's start by listing the coordinates of its vertices. -1, -2, 3, 1, and 2, -1. To find the coordinates of the new triangle, we can double these coordinates to get -2, -4, 6, 2, and 4, -2. Now that we know the coordinates of the vertices of the dilated triangle, we can draw in the corresponding segments. The 1 of 3 for this unit on dilations, similarity, and introducing slope.